All right, everyone, it's 1 o'clock. I guess we can get started. So I just about, I don't know, 10 minutes ago, finished putting together the midterm exam that I promised I would have for you today. And so I will send that out immediately after class. I think it turned out being, how many questions was this thing? I think it was 13 problems, but I'll open it up at the end of class and we'll talk about it at the end, okay? So hopefully I'll be able to save myself a few minutes to be able to go over that. So last time we were talking about 11.3, we were talking about partial derivatives, and then we were discussing higher order derivatives and different notations for those higher orders. And I did send out a video for the students that had stayed at the end and discussed that interesting concept of commuting the operation here. So anyway, that's out there. I saw some people had watched already, so hopefully it made sense. Did anyone, Daniel, did you watch that? Daniel, it was you that had the question, right?
Yeah, I was the one who had the question, and it did make sense. I was talking to my friend who had already taken Calculus 3, and he said, well, it does hold true. So I had kind of knew, and then I watched the video explaining it. It was a good proof. I liked it. You can kind of use it here because you can just rearrange the partial derivatives for B and then take it in respect to Y one more time for A.
Yeah, as long as the partials are continuous, you know, that's all we need. Or actually, we need the second partials, 2 of the second partials to be continuous. That's it. So, and in this case, because it's a polynomial function to start, all the derivatives will be continuous.
Yes.
So, but okay. So anyway, moving on, we still need to finish up this section. So the next quick topic here is something. This is like an application of partial derivatives. So this shows up later on in differential equations. You will see Laplace equations, and you know, all a Laplace equation is an equation. I mean, that's it. It's an equation just like x squared minus 4 equals 0 is a quadratic equation. A Laplace equation is a specific equation where you're trying to find a solution that satisfies this equation. So you know how we normally solve an equation like x squared minus 4 equals 0. And normally what we're trying to do is find the x which makes it true. So like in this case, we would say, okay, if we plug in 2, it would be true. If we plug in -2, it would be true. So in a quadratic equation, our solutions are just numbers, right? But in a Laplace equation, you have an equation where the things you're looking for here, the thing you're trying to solve, this is just this is the same exact thing, just using Leibniz notation versus the other notation. So what this is saying is, can we find an equation? Or sorry, can we find a function? Okay, so instead of trying to find a number that satisfies the equation, we're trying to find a function, u of x, y, that when we take the partial with respect to x twice, right? And then the partial with respect to y twice and add those together, we get 0. Any function that we can find that satisfies this equation would be a solution, all right? And this equation specifically is called the Laplace equation, all right? So let's see, just with an example, we're given a function of 2 variables, u of x, y, and we're asked to determine whether or not this function u is a solution to the Laplace equation. So all we're doing is trying to figure out whether or not it holds, right? Whether or not that holds the equality. Is this, so this is the question, is u of xx plus u y y equal to 0? Right, that's the question. So I need to go figure out what these partials are. So I'll do the partial of u with respect to x, which would be, let's call on somebody because we didn't get through many people last time. How about Daniela? Is Daniela here? I don't see Daniela. There's only, what, there's 15 people here? Okay. How about Axel? Axel here? Oh, wait, you know what? Sorry, I'm in the wrong class. I did this the other day too. I hit the wrong button. Okay. So how about David? David C? No David C? Caden?
Yep.
Okay, so I don't know if you had an opportunity to practice this partial stuff, but what would the partial of that with respect to x be?
The first partial with respect to x will be 3x squared plus 3y squared.
Okay, anybody disagree? 3x squared plus 3y squared. Anyone disagree? Everybody see that? Okay, you want to keep going? Okay, give
Yep.
me the second partial here.
The second partial will be 6x plus 3y squared.
6x. I agree with the 6x.
Actually, no, the 3y squared would be a 0 since y
That's
is a
right.
number.
Yep, okay, good. So that would just be 6x, right? All right, so that's this. So we have, this is 6x. And our question is, if we add that to this other partial, so we need the partial with respect to y. And Damian Duke can tell us that, maybe?
Yeah, I can.
Okay, go
It would
ahead.
just be 0 plus 3xy or 2y. So it'd be 6xy.
6xy. Okay, that would be the partial of this with respect to y, treating y like the variable and holding x to be constant. And then you go with respect to y again.
Yeah, it would just be
Okay.
6x.
6x. So these are equal, aren't they? But does it satisfy the equation? No, right? Not in general. Of course, if x is 0, right? If x is 0, then this would be true. But it would need to hold for all, values. So this in general is not true. All right?
Is that for every case? I'm so sorry.
What do you mean?
Oh, I was just wondering, for every case, you said it has to hold true for all numbers. So that would be for every equation that we're trying to find, right? The functions always have to.
Yeah, this would have to be 0 for all x and y. There might be y's in here too. So for every ordered pair that's in the domain here, every x and y that could actually be plugged into this, this
Okay, yeah.
equation would have to be true. So just
Okay,
because it
got you.
holds once doesn't mean that it's true all the time.
Thank you.
Adam, did you have a question?
What is this used for?
So there's several applications to this. I mean, it depends on where you are, like what course you're looking at. But mechanics, so that would be like engineering, right? heat dynamics, fluid flow. This is all really engineering. The Laplace equation, I would love to go into more detail because this is like real applied math, right? So, but we could just go off and be talking about it for an hour, all right? I think your best bet is to just Google Laplace equations and like, Google, where are Laplace equations used? And then I'm sure you're going to come up with all sorts of stuff. So, and there's other types of equations. This is Laplace. I mean, there's other equations that involve these partial derivatives where it's not necessarily plus in between these. Maybe it's minus, or maybe some other variation of this. And actually, in general, what we're looking at here are what are called differential equations, which is a completely different class than this class. You usually take differential equations after you take calculus. But the whole idea behind a differential equation is you're trying to solve an equation that involves a function and its derivatives. I'll just give you a very simple example. If I tell you I have a function y equals f of x, okay? Y is a function of x. And I want you to tell me what the y would be that would satisfy this equation. Okay, so you find me the function of x where this would be true. So this right here is called the differential equation. And the reason I call it differential equation is because it's an equation that involves a function f and its derivative is there too. And the solution is the function itself, whatever you can come up with. So can anyone just think off the top of their head what I could use for f of x that would make this true?
E to the x.
E to the x, right? Isn't e to the x its own derivative, right? I mean, that would be true, yes? So the function f of x equals e to the x would be a solution. That is a solution to that equation. Now, is it the only one? So you'd have to think a little more maybe. How about this function, f of x equals 0? Just a constant 0 function. Well, that's like trivial though, isn't it? I mean, 0, the derivative of 0, 0. This is like the trivial case. And most of the time we don't look at that case because that's a boring function. F of x equals 0 isn't doing anything. So that's like very, very loosely speaking, that's what differential equation is all about, is you're trying to find functions that are somehow connected to their derivatives. Okay, we're not going to go any further with that because like I said, we'll just get way off topic. All right, so we did that example. Now we want to talk about implicit differentiation. So recall from Cal 1. If we had something like, let's say we had x plus y, or let's say x squared plus y equals 5, and we were told to find dy dx. Well, we could do this very simply by isolating the y, moving the x squared to the other side, and then just differentiating both sides of the equation. So the left side, we take derivative with respect to x, we get dy dx. On the right side, derivative of 5 is 0, and derivative of negative x squared is negative 2x. And we'd be done. Right? That's just basic differentiation from Cal 1. Now, when you look at that and you compare it to something like this, this was a little bit different because if you try and isolate the y, you could take the x squared to the other side, but now you run into a problem because you have y squared, so you'd have to take the square root to get y by itself, but then you would have two different answers, plus or minus, right? So that basically forces you to look at two different scenarios. And so you've got to look at the positive case and the negative case and then do derivatives of those individually. So when we were in Cal 1, we called this right here an implicit equation. And this one over here, we called an explicit equation because you can actually solve for y and not have two different cases. So in Cal 1, we were taught how do you differentiate an implicit equation when it's not easy to get y by itself, or sometimes it's even impossible to get y by itself. So we were taught in Cal 1 that what you do is you just differentiate both sides of the equation with respect to x. And then just follow all of your differentiation rules. So if you have products, you do product rule. If you have quotient, you have quotient rule. If you have powers, you do power rule. If you have chain, right? Composition of functions, you do chain rule. So for here, what we would do is just differentiate. And since I have two terms here, I just do each one. And you're differentiating with respect to x. So the derivative of x squared would just be 2x. What about the derivative of y squared? This was the one that was, you had to pay attention to what's going on here. So what's the derivative of y squared with respect to x?
2y dy dx.
Y dy dx. Good. So that's us using the power rule, the two coming down, y to the first power, that's this. But then you have to take derivative of y in here with respect to x, which is basically your y prime or your dy dx. And then on the right side, you get 0, derivative of a constant 0. And then what you can do is you can isolate this by moving the other stuff to the other side. So, subtract 2x and then divide through by 2y. You wind up getting negative x over y. So that would be your derivative. Does that ring a bell from Cal 1? Okay, so now what we want to do is we want to see, can we do the same thing when we are talking about surfaces in three-dimensional space? So that's what this next note is about. Let's say we're given something. Now this is an equation that has three variables in it, right? Now, remember we talked about quadratic surfaces where you had like spheres and ellipsoids and hyperboloids of one sheet or two sheets and all those different things. Here, that's not what we're looking at because this is like x cubed, y cubed. So these are cubic. So these are not, this doesn't fall into that standard category of surfaces, but they still are surfaces because they contain all three variables x, y, and z. So the first question is, can we figure out the rate of change of z with respect to x? And do you see that it's a partial derivative? You see it's partial? The reason it's partial is because if you ever wanted to know what z was, right, what two things would you need to know? Like
X and Y.
Yeah, I can never solve for z unless I had x and y, right? So what you could say is like z depends on x and y. And since z depends on x and y, you're always going to be talking about partial derivatives when you're looking at derivatives for the function, because z depends on two other things. So that means you have to hold one of them constant and let the other one be the independent variable. All right, so how are we going to do this? We are not going to try and solve this for z. Okay, we're not going to try and solve that for z and make it look like, like this right here. This is basically saying z equals this. And then when we do partials, we just do what we were doing last class. But in this problem, we can't do that. We cannot easily get z by itself, right? Because there's a z here and there's a z here, z cubed. So it's not easy to get z by itself. So here's what we do. This is called implicit differentiation. It's going to be just like we did in Cal 1 with a couple of different little catches to it. So what we're doing is we're saying we'd like to know the rate at which z changes if we change x a little bit. So if we just adjust the value of x just a little bit, how much does the z value change? Well, in order to figure that out, we have to hold y constant. All right, so this is going to mean for us that y here is constant and x here is the variable. And now we differentiate on both sides. of the equation with respect to x. So the way I'm going to write that is like this: taking the partial derivative with respect to x on the left side of the equation, and then I'm going to take the partial with respect to x on the right side of the equation. Now the right side's easy, right? Because that's a constant. Derivative of constant is 0. All right, let's start working our way across the left side. So we have here 1, 2, 3. We have 4 terms, right, separated by additions. So we can just differentiate term by term. So let's see. Margie, what's the derivative of x cubed?
The derivative of x cubed with respect to x is going to be 3x squared.
And that's it, right?
That's it.
That's it. Okay. Now, Margie, keep going. Plus, now what's the derivative of y cubed with respect to x?
Since it's all by itself, it's going to be 0.
0,
Because
because it's a constant, right? Because y we're treating like a constant, so the derivative of that will be 0.
Mhm.
Okay, you want to keep going?
Sure. And then for Z3, that's interesting. Okay. It's not a constant, so you would go ahead and differentiate it as well.
Yep.
So it would be a 3, let's see, 3z to the square. 3z squared.
Okay. Now we
Okay.
still have to pay attention to the z though now, right? We've done the power.
Oh,
rule.
yes, that's right, because we talked about that back in the earlier Cal example. So it's going to be differential of z with respect to x.
Exactly. And when we say that it's a partial, right?
Partial, right.
Partial derivative. So it's going to be, we're taking the partial derivative of z with respect to x. And that's just like the y was when Benjamin earlier said, you know, like the derivative of y squared was 2y dy dx. Same exact concept. Good. Okay, let's go to, is Daisy around?
Yes, I'm here.
Okay, Daisy. You get the harder part here. Oops. So what do you think about this, Daisy? You have to take derivative of this. And remember, y is a constant, right?
Would
Okay.
it just be 6y?
Let me write it down here. We have 6xyz, but remember that the y is a constant. So I'm going to bring it out here in front like this. Just remember that's a constant. And when we take derivatives of constants that are attached to functions, when we take derivative, they just come along for the ride, right? Daisy, yes?
Yes.
Okay, so I should have just 6y here. But then I have to be concerned about taking derivative of x times z. So Daisy, how would you take derivative of x times z? What rule do you think you're going to need to use? What's the operation between them?
Multiplication?
Okay, it's a product, right?
Yes.
So how do you take derivative of a product? What rule do we use in Cal 1?
Is it the product rule?
Product rule, right? So we have to do a product rule on that. So I'm going to do a set of parentheses here because the 6y was a constant that was going to come along for the ride. And now Daisy's going to help us do the product rule on this. So the product rule says take derivative of the first one. So Daisy, what is the derivative of x with respect to x?
Just 1?
1, okay. And then times the second function, that's product rule. Plus, now Daisy, what's the derivative of z with respect to x? Or I should say partial derivative. That's not 1, right?
No.
It's not 1, but it's just like it was when Margie was saying the derivative of z here, right? It should pop us out a little partial of z with respect to x. And we're almost done, right? We have to finish off the product rule. So we multiply that times the x. Daisy, does that make sense?
Yeah.
Derivative of x is 1 times z plus derivative of z with respect to x, which is partial of z with respect to x, times x. And that's it. We're pretty much there. I mean, we have work to do, but we have the partial of z with respect to x, which appears within this equation. And so the rest of this would just be algebra. It would just be moving things around until you could get partial of z with respect to x equals something. Should I go through that work, or do you feel comfortable that you could solve for partial of z with respect to x? What do y'all think?
I think you should go through it just to be
You guys go
safe.
through it? Okay, I'll do it on this one. On the next one, I won't. Okay, so here's where I am. I've got 3x squared plus 3z squared partial z with respect to x plus, now on this 6y in front of the parentheses, I'm going to distribute the 6y through. So I'm going to have 6yz, and then I'm going to have plus, let me write it this way, 6xy partial z with respect to x equals 0. So that was just distribution of that through the parentheses and kind of rearranging things around. Now what I'll do is I will take everything that has partial of z with respect to x, I'm going to leave it on the left side of the equation. Everything that does not have it is going to go to the right-hand side. Okay, so I'll have negative 3x squared. I'll have plus 6yz. No, minus, sorry. So I brought this over and I brought this over. And why is it that I take everything that doesn't have partial z with respect to x to the other side? Why am I doing this? What can I do now?
You're trying to keep partial z over partial x onto one side.
So
you
I
have
can
to
do
factor
what?
that out. So you can factor the partials out.
Yep, so now I can, since these both have this partial in it, I can factor it out. Oops. And once I have the partial factored out, then I can just divide both sides of the equation by this. And I will have an expression for partial of z with respect to x. Okay, so there we go. Now, let me just try and help kind of wrap your head around what we've just done. All right, like what does this represent? Well, this up here is a surface, right? In three-dimensional space, it's a surface. I honestly don't know what that looks like, okay? So I'm just going to kind of make it up that it's three-dimensional. And just remember, it could be, you know, like spherical or, you know, sheets or whatever. Let's just say it's just some three-dimensional shape, right? Or some shape in three-dimensional space. What we said is, or what we found here is that if we go to some point on that surface, call it X, Y, Z, and we have to be on the surface, which means that that X, Y, and Z must go into that equation and give you something true, right? So it has to be a number that we can plug in here for numbers for X, Y, and Z that would plug in and get you 1 when you got the answer, all right? So if we go to a specific point on the surface that satisfies this equation, then if you want to know the rate at which Z is changing, if you change X a little bit. So remember, this is all sitting in like three-dimensional space, right? So you have like an X, a Y, and a Z. That's kind of how we get to that point. I missed it. Okay, so we're saying if you go some X, Y, and Z, then if you want to know how rapidly the z coordinate is going up or down there, if you change the x, so the x is down here, if you change the x from left to right, infinitesimally, just move x just a little bit, this equation down here, that function will tell you the rate at which you're going up. So it's the instantaneous rate of change in the z coordinate when you change the x just a tad. Now, when I say a tad, I'm saying like infinitesimally. And that's what that is. So if you want to know what it is exactly, then you have to just take the x coordinate from here and plug it in, the y coordinate and the z coordinate, and it'll give you a number, and that number will give you the actual rate of change. Does that all make sense to everyone?
You said rate of change of z, but in relation to x?
In relation to x, and that's why, I don't know if you can see it here, I drew a little arrow down here going left and right.
Oh, I see.
That's, oh shoot, I drew that backwards, I'm sorry. Do y'all see I drew that backwards? Oops, sorry, x goes this way. My fault, my fault. Glad you asked. If I change x just a little bit, see, but we're holding y constant, right? So the left and right is actually not moving. I'm running out of colors here. We're holding the y coordinate constant, and we're changing the x coordinate just a little bit and seeing what happens with the up and down on the z. So it's like when we cut through with a plane and it created a curve on our surface, we're finding the slope of that tangent line. That's from last class when I showed you that picture and we sliced it and looked at it from the side and it was just a curve. That's exactly what we're doing. The big difference here is that this equation doesn't have to be a function, which means it would fail like that weird sort of vertical line test in three-dimensional space. It could be a sphere, right? Was there another question?
No, not really a question. It's just an observation. It kind of helped you figure out like the sort of like, yeah, the slope of the tangent line.
Yeah, yeah, but only in one direction. That's the thing. It's only in the direction that is running parallel to the xz plane, because we're holding y to be a constant. Okay, let me, oh shit, that's not what I meant to do. I wanted to actually copy this whole thing. Just save it for later if I need it. Okay, now I'll clear it. All right, so the next one, let's see, how would we do this next one? Partial of z with respect to y this time, we do the same thing, both sides. This time, because we're doing it with respect to y, we're holding x to be constant, right? So if we hold x to be constant, oops, I forgot my derivative over here, partial with respect to y of 1. The right side will be 0. And then let me give myself some room here. Derivative of that will be what? Derivative of x cubed.
0.
0.
Right? Because x is a constant. So there's going to be 0. And now this one now is not 0. This one is 3y squared, then times the derivative of y with respect to y, which is 1. So it's just 3y squared. And then we have plus 3z squared partial z with respect to y this time. So here we have to use the chain rule, take the power down, and then take derivative of z with respect to y, which is this. And then on this, the x is constant, so I'm going to look at the x as being out here with the 6, and then I have to do product rule on the yz instead. So the derivative of y with respect to y would be 1 times z, then plus the derivative of z with respect to y, which would be partial z with respect to y times what? Y, right?
Yeah, just y.
Are there any questions? I went through that a lot faster than the last one. Your goal now would be to get those on one side of the equation. or get that on one side of the equation, which would be very similar to the algebra we just did. So I'm not going to go through that one. Okay, so this is the end of the section. And so basically what we've learned in this section is that, you know, if you have z is some function of x and y, that we can find the partial of z with respect to x and the partial of z with respect to y. And to do that, we just hold, in this case, the y constant and take derivative, or we can do, in this case, hold the x constant and take derivative. This is the easy case because it's already solved for z. But if we can't solve for z, if we have, you know, basically some equation equals 0, let's say, and this has x, y, and z in it, and we can't get z together easily, so this is an implicit equation, then we'll have to do the partial on both sides with respect to some variable, whether it be x or y. We'll do it on one side of the equation, and we'll do it on the other side. It just depends. It depends what we're doing the partial of, you know, with respect to x or y. Does that make sense? Yeah?
Yes.
Okay. So that's pretty much it for that then. Let me try and I'll just snap this again just to have it. And with that done, I'm going to move on. All right, so the next section is going to be pretty quick. There's not a whole lot in this next section that we're going to talk about, but it's a very nice result. Okay, so the whole idea here, like not the whole idea, but one of the major consequences of what we've been talking about is that we now are going to be able to look at some surface, and we're going to be able to go to some point on that surface. Okay, so we're just going to pick some point on that surface. Let me kind of bring the surface up so you can kind of see through it a little bit better. Okay, so everyone see that point on that surface? At every point on this surface, there should be a tangent plane. Whoa, I don't know what just happened. It's got flipped over. Okay, there it is. Make this a little bit bigger. Okay, so does everyone see that we have a plane that is tangent to the surface at that point? And as I move that point around, man, that's really messing things up. Why is it doing that? As I move that point around the surface, doesn't matter where I go, I'm going to have like a different tangent plane, right? Now, the way that we can figure out what that tangent plane is, I told you all this in class last time, is, or one way to consider it is, we already know that we have a point on the surface, right? It's the point we're talking about. And for a plane, all you need is, right, for a plane, all we need is a normal vector and a point. And once we have that, we're in business. So if we already know the point we're talking about, we've got the point taken care of. So all we need now is the normal vector, right? So somehow we should be able to get this normal vector. And we just figured out that the partials give us some sort of like direction, right? The partials give us, like in one direction, it gives us a tangent line, and then another direction gives us another tangent line. And somehow we can use that slope, those two slopes, to be able to define the plane. All right, so that's the general idea in pictures. Let's just get to the actual formula here. So this says, if z is some function of x and y, so you've got some surface, right? And f has continuous partial derivatives. I misspelled that there. Has continuous partial derivatives. Then the equation of the plane, which is tangent to the surface at some given point, x naught, y naught, z naught, is this equation right here. All right, so remember, the equation of a plane, in general, the equation of a plane is a x minus x naught plus b y minus y naught. We learned this back when we were studying planes, right? Like that's the general equation of a plane, where x naught, y naught, z naught is just a point. And then what was the ABC? Do you remember what the ABC was? Or where it
The
came
normal
The
vector.
norm-
Direction.
That was the normal vector. Whatever that vector was, the A was the X component, the B was the Y component, and the C was the Z component, right? So whatever those numbers were, we just stuck them here, here, and here. So when you look at this equation right here, do y'all see that that is that equation? Do y'all see that it is the same equation? With this exception, this right here is our A. This right here is our B, and -1 is C. -1 is C. So it's saying that in order for us to figure out the normal vector of the plane, all we need to do is figure out the partial of f with respect to x. So we're going to take the partial of this function with respect to x, and then we're going to plug in the point we're talking about, the x naught and the y naught, and that's going to give us a number. That's like a slope, right? And then we're going to take the partial of that function with respect to y and plug in the point we're talking about. That'll give us a different slope. And those happen to be the components of our normal vector. Now, why do you think the C is -1? Why do you think that's always -1?
Probably because never mind, I give up.
Looks like we're always taking respect to z, so I mean the derivative, like I don't, because like if you're taking the derivative on both sides, then you're going to be getting just dz over, I don't know.
Yeah.
It's weird.
So think about it visually. Think about it visually. Maybe it'll be easier if you think about it from the perspective of this is a function of x and y, right? Z is a function of x and y, which means it must be a surface, right? It must be a surface. And it must pass that sort of weird vertical line test, right? Where you have the ground down here. So points go in, points go up, we have a surface here. So think about the normal vector for that plane, the tangent plane that would be there. Do you all agree that the x component, this piece, that we should have some slope, right? It's, you know what, here, I have a better idea. Let me think about how I want to do this. Yeah, maybe. Okay, this might work. Give me a moment to find the file. Where are we? 10-4. So I mean 11-4. So 11-2. No, sorry. It was 11-3. Yeah, here we go. All right. So when we had this picture here, and when we fixed the y, we had this plane cut the picture that way, right? That's us fixing y to be constant, and then we had some direction like that, right? And then if we fix the x, it does a plane this way, and like that, right? So if we were to cross those two, vectors, so do y'all see those are kind of like vectors? If we were to cross them, I need a different color here. I'm going to do an exaggerated cross product. It should stick out like this, and it should be orthogonal to those two, right? Something like that. Okay. This vector lives in three-dimensional space, right? This blue vector. And I wish I could move this graph around because I want that blue vector to move around with me. I'm going to try and do it anyway. I'm going to try and just spin this around. If I were to spin this around, okay, and just come look at it from another perspective, like over here, and look at that vector again. The z component of that vector, the z component will always be pointed straight down. Remember, the normal can come out this way too, so maybe it'll be better if I look at that. The z will always be pointed straight down because the surface never turns to the side. Like you never get like the side of a sphere. It's always got to be. Gosh, it's so. Trying to think of a way to explain it. I think it's because you can look at it as like the vertical line test. If I pop a vertical line through this, it's going to hit the ground somewhere, right? And I only hit it one time. So because of that, any vector that's going to come off of that point is going to have a z component that either goes straight up or straight down. It's got to be one or the other. It's impossible for us to have a vector, a normal vector that would come out sideways, right? If it came out completely sideways, then the z component would be 0. But that's impossible because then the surface would have to be like vertical like that, and that would no longer be a function. Okay.
I'm so sorry.
Go ahead.
I was just gonna ask, so can this, you said that sometimes it can be pointing upwards. Does that mean you can make it +1, or is it like stupid to think that is it always gonna be -1?
Well, you could make it +1, but what would happen if you make it +1 is that these would have to be minuses.
Okay.
You know what? Let's do this. Let's time out on this, okay? Because in about a section from 2 sections from here, we're going to have a more general formula. See, because right now we can only find the tangent plane to a surface is if that surface is a function of x and y. So we have to be able to solve for z. 2 sections from now, we're going to get a formula that's going to allow us to find the tangent plane for any surface, even if it's a sphere. And when we get to that formula, this -1 will become much more apparent as to where it's coming from. So I was making an attempt to explain why this is -1, but I think it's better right now if we just hold that off and let's just make a mental note.
So it's just
-1.
So in this, so it's the consequence of that formula, that when you apply that formula to z equals f of x, y, it's going to become -1.
That's right. Well, if we can solve for z, then we're guaranteed this will always be -1, always. But to see it, yeah, let's just cross that bridge when we get to it. I think it'll be easier. So look, here's what we're saying. At the end of the day, the normal vector to the tangent plane is just, this piece here in front. This is our A, this is our B, and then our C is always -1. And so that's what I put here, right? Let's do an example. Find the equation of the plane, which is tangent to this surface at this given point. All right, so let's do this. So what do I need to know? I need to know that this is x naught, y naught, z naught. They've given us the point on the surface. And now all I need to know is the normal vector. So the normal vector will be the partial of f with respect to x at the point 1, 2. Then the partial of f with respect to y at the point 1, 2. And then the third component will always be -1 because it is a function of x and y, right? It solves for z. Do you understand this notation? We're going to take the partial of f with respect to x, and then we're going to plug in 1 and 2 for x and y respectively. And then the same thing here. We don't really need this z. We don't need the z for our formula. So the partial, let's do the partials. The partial of f with respect to x should just be 1/2 y. And so if I plug in 1 for x and 2 for y, I should just get 1. Then the partial of f with respect to y would mean we're going to take the derivative of this, hold the x to be constant, right? And treat y as the variable. And so that gives us 1/2 x. And if we plug in 1 for x and 2 for y here, we get 1/2. Any questions on that? This is an easy partial derivative problem, right? It's not very complicated to take the partials. All right, so let's take a volunteer kind of. Abi, are you here?
Yeah.
Okay, so will you give me the equation then? Are you ready? Do you have any questions before, or do you think you can give me the equation?
So the equation is 1 times x minus x naught.
Okay, yeah, so 1 times x minus, now what's x naught for us though? That comes from the point, right? That comes from the point we're looking at.
So it's 1.
1, okay. And then now we have plus
1/2 times 1. 2 y minus 2, sorry.
minus 2. Okay, good. And then we're almost there. Always -1, right? This last piece is always -1, and then
Z minus 1.
there you go, equals 0. And that's it. That's the equation of the plane. So oops, I didn't mean to do that. If I go and graph this surface, right, which I'm about to do on the computer, if I go graph this surface, which was this thing we were looking at a moment ago. Let me go back, let me just rerun this cell here. Take us back to the original. Can I clear this out? Everyone have the equation? Okay. So if here's our function. We're going to go to the point, what was it, 1, 2, 1 or something like that. So that's this point right here. There it is. And then I'm going to graph the tangent plane. Here it is. This thing always wants to flip over. And I'm going to have the computer show us the equation of that plane, which is negative. Oh, they simplified it. So they distributed through and cleaned it up. So we should, yeah, we didn't do that part. But if you distribute all those coefficients through the parentheses, you should get x plus 1/2 y minus z. And then if you take this 1 to the other side, you'll have equals 1. All right, that was just a problem to get us, you know, like somewhat familiar with it with an easy function. Let's do a harder one. So for this one, I think I'm going to give everyone some time. All right, we're going to do the same exact thing, but the derivative is going to be a little more complicated. Just a little, I mean, it's not like real complicated, but it's a little harder than what we just did. So how about we take 6 minutes or so? See how far you can get in about 6 minutes. I'm gonna start working it while you're there, and then you can kind of look to see if you're getting the same thing. All right, I've shown the work there. Does anyone have any questions on that work?
Yeah, I have a question.
Yeah, go ahead.
So can we leave it in the original form after we get the answer, or do you want us to simplify?
No, you can leave it like this. It's
Okay.
still the equation of a plane, so that's okay.
Okay.
Yep.
I also have a question. On the y, shouldn't that be a 2? Oh no, never mind. 1. Yeah.
Yeah, you see, because of this bottom is 2. Yeah.
Mhm.
Any others? Okay. All right, then I'm just going to proceed. Let's clear it out. I think I have a graph of this one. Yeah, so this is, I think that's a really cool looking surface. Wouldn't you agree? Whoa, hold on just a second. My TV turned on all of a sudden. Okay, that's a cool looking surface, yeah?
Yeah,
it's cool.
It's interesting.
Yeah. So let's go to the point we're talking about. So here's the point. There it is. Let me bring that surface out of here a little bit so you can see it. Man, my computer is running slow. I must have something else hung up. Oh, well, I'm about to close this out, so that's okay. So there it is. And then here comes the plane. Wow. Okay. There it is. And that's the plane that's tangent to that surface at that point. And then the equation is here. Now it did some rounding of a decimal because it had pi over 4 in there, so it just got the decimal. All right.
So that tangent plane, that's like the only tangent plane that exists for that point.
At that point, yeah. So it's the plane that just touches through that point, right? Of course, it's going to hit the surface in other places, but that happened even in Cal 1. We had, we could have a tangent line right here that would hit in other places, but that doesn't matter. We're looking for like the line that just passes through that single point. We're doing the same thing here, but for a surface in 3-dimensional space. Does that make sense? That there's a plane that behaves like that?
Yeah.
Okay. All right, moving on. That's it. So there's just a couple of problems from that section for homework. Just doing the same thing we were just doing. It's pretty straightforward. As long as you knew the partial derivatives, everything's straightforward. All right, I'm going to close this one out. Let me do some. I'm going to close this out. I'm going to close this whole program out because I think it's slowing down. And that does it for 11.3 and 11.4. So now we're going to start 11.5. And for 11.5, I want to start by just reminding you about, in Cal 1, like the most important differentiation rule that you learned, the one that was for most people the hardest, and that was the chain rule. Right? The chain rule from Cal 1. The chain rule in Cal 1 said that this is the formal way that we write it. If y is some function evaluated at some other function, so you have functional composition, you have g inside of f, then the derivative of this will be the derivative of the f function evaluated at g times, this is where the chain comes in, the derivative of g evaluated at x. For example, if we had y is equal to sine of x squared plus 1, then we could look at the outer function being the sine function and the inner function as being the polynomial x squared plus 1. And then to take the derivative, you're just taking the derivative of the outer one first, which would be cosine. And then you plug into it g without taking the derivative, and then you multiply times the derivative of what's inside there, which is your 2x, right? So that's the way we did it in Cal 1. But the ultimate idea that I want you to see right now is that when we were doing this in Cal 1, when you go back up here, or you could look here if you want, in order to know what y was, all you have to know was what x was. So y depends on x only, right? So if I were to draw it like this, what I mean by drawing this is that to know what y is, you would have to know x. So it's kind of like the x is going to feed into the y. If you feed the x into the y, then you can figure out what y is, right? Okay. So all I want to say about that, let's talk about chain rule here in Cal 3. So for chain rule here, we need to be able to handle functions that have several inputs. So back in Cal 1, this is what I just said. If you had y as a function of x, then y can be determined if x is known. So if you give me x, I can give you y. And when you have that relationship that y depends solely on x, then we have this idea of a derivative. You know what? I want to do something real quick. I want to see if I can just quickly push this into my OneNote instead of doing it there. You all ready for spring break?
Yeah.
Oops, wrong.
I'll make 2 springs where we've effectively had 2 spring breaks.
Yeah. Where's one?
That was just like last spring semester.
Yeah, because the COVID thing, right?
Yeah, we lost the week right after spring break.
Oh man, is that gonna bring it in sideways? Okay, I guess it's not happening. All right. We're gonna have to stick with this, sorry. So if y depends on one variable, then there's only one derivative possible. That is dy dx, right? Now, an example we could do here, I'm not gonna go through this example, is that y here depends on x. And so we can actually ask you for dy dx and it would just be 2x plus 6 and you're done, right? But what if you have something that looks like this? I need to zoom out of this. Where's my zoom? There it is. What if instead you have that y depends on y is some function of x, but then that x is some function of t. So y depends on x, but then x depends on t. So in order to know what y is, you have to know what t is, right? Because t gives you x and then x gives you y. Well, whenever you have that, then there's still only one derivative possible. The derivative that's possible is the one that shows the rate of change of this with respect to this variable, which is dy dt. But to get to dy dt, what you do is you first look at this intermediate relationship between y and x, and that has its own derivative, dy dx. And then you look at the relationship between the x and the t, and that has its own derivative, dx dt. And the chain rule says that if you multiply those two together, right, that's what the big derivative is. The derivative relating y to t is equivalent to the derivative relating y to x times multiplied by the derivative relating x to t. That's the chain rule. That's really what chain rule is in Cal 1. All right. So we're going to do an example of this one. So y here is x squared and x is sine of t. I want us to find dy dt. So I'm going to do this a little different than what you're used to seeing, okay, because of where we're headed, all right? So the way I'm going to write this is, look, right now I realize that y depends on x, right? I know that from this. To know what y is, I have to know what x is. But when I look at x, x depends on t, so I know that x depends on t. And so if I want to know what the relationship between how much y is changing with respect to t, I first have to look at the intermediate derivative here, dy dx, and then the intermediate derivative here, dx dt, and I will multiply those two together to get this relationship, which is dy dt. So it should be dy dx times dx dt. Any questions on where I'm coming up with that? Now we just do them. What's dy dx? So if you just look at this equation, and this is your whole universe right here, you're not looking anywhere else. Dy dx, you take derivative with respect to x on both sides, and you should just get what? 2x?
2x.
Okay, times, now I need dx dt, so now my whole universe is this equation. And I'm doing derivative with respect to t on the left, derivative with respect to t on the right. I didn't show that on the previous one, maybe I should have, but I'm taking derivative with respect to t on both sides. So left side is dx dt, which is this, and that will just be the derivative of sine of t with respect to t, which is just cosine t. Now, there's one more thing I can do. Right now, my answer has x and t in it, right? X and t. Since I wanted to know how the rate at which y is changing with respect to t, it would be nice if everything was in terms of t. So let me get rid of this x and replace it with something that has t in it. But I know that x is sine of t, right? That's what x is. So I can just write 2 sine of t cosine of t. So just replace that x with sine of t. And now my derivative, dy dt, is that. Now, yes, I realize that's an identity. We can clean that up, but we don't need to. All right. Any questions here? I'll point something out real quick. If you would have taken this y and you would have said it's x squared, right? But x is sine of t. So take sine of t and plug it in right here. Wouldn't you get sine squared t, right? It's just sine of t, but then you square it. And if you do this and I ask you to take derivative with respect to t, you would go, okay, dy dt is equal to, then you do chain rule, right? The 2 would pop out. So 2 sine t times, then you take derivative of sine t, which will give you cosine t. And that's exactly the same answer, right? I'm just trying to show you a different way to approach it because, again, of where we want to go with this. All right. So how about this scenario? We have z now depends on x and y. So z is a function of x and y. Z can only be determined then if you know both x and y, right? You have to give me the x and give me the y, then I'll know z. So now what I have is a different sort of drawing. My z, to get it, I have to know x and I have to know y, right? Both of them. So they both feed into the z. What we're starting to draw here are called trees. Okay, so we're going to start learning how to draw these trees to do derivatives. And so this is the first time that our tree actually has 2 branches that go down. And anytime you're interested in knowing how something up here changes with respect to something down here, if I want to know the relationship between those, right, how much z changes if I change x, I have to do a partial derivative. And it's because this has to be fixed. I have to fix the y. I have to hold it constant to be able to talk about this. I can tell you how much z changes. You know, if x changes a little bit, I can tell you how much z changes, but you can't be changing the y on me. You got to leave the y alone. Fix it, right? So down this branch, we can only do a partial derivative. Similarly, if you want to know the relationship between z and y, then you have to go down this branch, and that would also have to be a partial derivative because then you would have to hold x. So if z depends on 2 things, there are 2 possible derivatives you could talk about. Partial of z with respect to x, partial of z with respect to y. That's it though. Those are the only 2 possible. We've done this, right? We've already done, I mean, that's what we've been doing the last few days. We're just trying to get to a point where we can really generalize this. So here is an example that we've already done, right? This is like previous problems. We have that z here depends on x in here, and there's a y in here. So I know that z depends on x and y. And because z depends on 2 things, I know the only thing possible here is a partial of z with respect to x and a partial of z with respect to y. And that's it. So to get those, I'd have to calculate each one. So let me do partial of z with respect to x first. To do that, I'm going to have to hold y constant. So I'm just going to fix my y to be a constant here and take the derivative of this. So do y'all see I'm going to have to do product rule because I have x times sine of something. So product rule would give me 1 times sine of xy. And then plus, now I take derivative of sine of xy, which is cosine of xy, times chain rule, the derivative of what's inside with respect to x. So who wants to tell me what, well, don't know. How about Lorraine? Can Lorraine tell me what derivative of x times y is with respect to x? Or is Lorraine not here? No, Lorraine? How about Fabiola? Oh, wait, I called you last time. How about Adam?
The derivative of what again?
Want a derivative of x times y because I'm doing chain rule here. So I'm trying to take derivative of x times y with respect to x.
So it would be y.
Y. Good. That's it. Okay, so this right here, oh wait, I'm not done. What do I need to add one more thing on here. Almost forgot.
Plus c.
Nope.
Or no, not plus
X.
c.
X.
Plus x
Times x.
times x.
Yeah, so we have derivative of x times the sine thing plus derivative of the sine thing times the x. So that's our product rule. So that's one of the partial derivatives that's possible here. The other partial derivative is now treating y like the variable and x like the constant. And that's good because if x is a constant, I don't have to do product rule. Do y'all see that? If x is a constant. So I can just do x comes for the ride times, let's see, sine, derivative of sine is cosine of xy, times, now I take the derivative of the inside with respect to y this time, which would be x. And that's it. Any questions? That's not new yet, right? I mean, that's stuff we've done. Okay, well, what about this though? This we haven't seen. What if z is a function of two variables, x and y? So z depends on x, z depends on y, but the x depends on t and the y depends on t. Then think about this. What would you need to know in order to find z?
You would
To
need
know
to
what
know
z
X
is.
and
I would need to know x and y, but what do I need to know x?
T,
And y?
also T.
T. So to know z, I just need to know
You just need to know T.
you just need to know t. Because if you give me t, t will give you x, but t will also give you y. And then once you know x and y, that gives you z. Do y'all see that? This is different than the last problem because now instead of needing to know two things to get z, I still need to know two things, but those two things I can get if I know what t is. So ultimately here, z depends on really only one thing, right? T is the same thing down there. So z depends on t. And because z depends on t only, there's only one derivative possible, and that is dz dt. I mean, sorry, that's a typo. Hold on, that's a typo. That's a typo. It is, that should say dz dt. We should be able to figure out the rate at which change, the way, I want you to try and think of derivatives this way. Like, if we just like take the value of t and just nudge it a little bit, just change the value of t, just move it a little bit. The question is, how much does z change by, right? That's what the derivative represents. So this is saying, look, in order to know how much z changes by, I only need to nudge t. That's all I need to do. Just nudge t, both of those nudges will nudge the x and the y, and those nudges will nudge the z. So here, the only derivative possible is dz dt. And notice those are not partials. They're not partials because they do not depend on two different things. You don't have to hold anything constant here. Nothing ever has to be held constant. So the question is, what is it? Okay, and this is where this is new. What is it? What is dz dt if we have this relationship? So look at this. To get from z to x, you have to know that partial, right? Because you have to hold y constant to get from here to here. But then to get from x to t, since x only depends on t, that's a straight derivative. I call these partial derivatives and I call these straight derivatives. I don't even think that's a mathematical term that's appropriate. Like, I've never heard anyone say straight derivative before, but it's my way of distinguishing between a partial and a not partial, okay? And the d's look straight instead of curved. That's the way I think about it. So from z to x has to be a partial, but from x to t has to be a straight derivative. And then if you go down this side, you've got a partial here, and then go here and here, you have a straight derivative. This derivative is just, now you have to pay attention to this, the derivative we're looking for, dz dt, is just, I'm looking for a color here. I only have 3 colors that I'm working with here. Okay, so this dz dt is going to be this branch of the tree multiplied together. That's this piece right here. Okay, so it's dz dx times dx dt. Then you add to it the product down this branch, dz d partial z with respect to y, dy dt. And if you take that branch here and that branch here, multiply down the branches, add the branches together, that will give you this derivative. That's the way chain rule works when you start to have more variables that depend on other things. I think it's worth it for us to see an example.
So I have a question then real
Yes.
quick. So
Mhm.
if X and Y both depend on T, can't we, if we wanted to, technically rewrite this as a 2-dimensional function where Z is purely in terms of T and then
Yes.
just, and then we have our simple derivative?
Yep, that's exactly right. And that is why this is a straight derivative and it's not a partial. Because ultimately, it's like all this X, Y stuff is just like gibberish in the middle. The real relationship we have here is between Z and T. So it is like Cal1. It's like
Yes.
saying Y depends on X, right? Here we're saying Z depends on T.
All right. So that seems fairly simple.
It is, but let's look at it. Let's look at the example, and then I guess
Okay.
you'll see how. So, here we have Z as a function of 2 things, X and Y, right? Z is X sine X, Y. And then we have that X is going to be T squared plus 1, and we have that Y is going to be a natural log of T. So I think, Daniel, what you're saying is, can we just like take X here, take T squared plus 1 and plug it in here, and then replace the Y with natural log of T, and then just differentiate that?
Yes.
Yes, and the answer is yes, you can. Yes, you can.
Yeah, but I don't want to do that with natural log.
Well, I think for this problem, it wouldn't be that bad. It gets worse when you start looking at trees that look like, where you have maybe one variable depends on 2, and then each of those depends on 2, right? Or maybe you have one that depends on 3, but each of those depends on 2, but each of those depend on 2, right? So like this tree doesn't have to have just like 2 levels to it. We're trying to generalize this. You could have as many levels as you want with as many variables being dependent upon others. Does that make sense? So this is more about a procedure of how to create the derivatives and talk about what's possible rather than just, let's just get it all back to Cal1, because we can't always get it back to Cal1. Okay, let's do this. So the way I'm going to do this, I'm going to start, well, you know what? Why don't you start? I got to take a quick break. I can't wait anymore. You draw the tree and see if you can start talking about what the derivatives down that tree look like. Okay, I'm back. So we have z depends on x and y, and x depends on t, and y depends on t. So when I look at this, the way that I think through this is I say, okay, when I go from z down, I split. And since I split, they have to have partials. So this has to be partial z with respect to x, partial z with respect to y. Now, when I go from x to t, there's no split there. So that's just going to be a straight derivative, dx dt. And then over here, same thing on the y, dy dt. Now, because I have two branches that I have to go down, right? Two branches. Then to figure out dz dt, I have to take the product down this branch. I almost did partial there. And add to it the product down the other branch. Oh, I did it. And now it's just a matter, once I've got that written down, it's just a matter of going up here and looking at these and taking derivatives. So I start out by saying, what's the partial of z with respect to x? So I have to take partial of that with respect to x, which we did, I think, in the previous example, didn't we? Partial of that with respect to x?
Yeah.
It would be, I'm just going to put in parentheses, it would be 1 times sine of xy plus cosine of xy times y times x. Okay, so that is the partial of this with respect to x. We have to do product rule. But then I need dx dt, multiply times that. Dx dt, I go up to the equation with x and t, and I take derivative with respect to t on both sides, and I should just get 2t. Any questions on that? Then that's the product down the first branch, the one on the left. Now I add to that the product down the second branch, which is dz dy. So I take derivative of this with respect to y. We did that in the previous example also. It was x cosine of xy times x. That's derivative of this with respect to y. And then we do dy dt, so derivative of y with respect to t. Derivative of natural log of t is 1 over t. Now, on your exams, I would accept that as an answer. Okay, that would be okay. But if you wanted to, you could get everything in terms of t now. So that means you would have to go in and replace all your x's with t squared plus 1. And replace all your y's. I forgot my x's over here. All your y's would be replaced with natural log of t. And then everything would be in terms of t. You don't need to do that, that's what I'm saying, but you need to be aware that that's how you would get everything in terms of t only. Any questions? I think we have time, just time to do one more. And that's this one here. So what if z depends on x and y depends on s and t. So this time s and t instead of just t, right? And sorry, did I say y? X depends on s and t, and then y depends on s and t also. So when you look at this, at the end of the day, can you give me z by giving me one thing?
No.
No, you have to give me two things, right? Which means that there are two partial derivatives possible. They're not straight derivatives. You look back here. Here on this one, z depend on x and y, x depend on t, y depend on t. So at the end of the day, z just depends on t. And if z depends on t, that's a straight derivative. Here, because z depends on two things, the only thing possible are two partials. And I'll explain what they are, but let me just kind of draw a picture. One thing I could have is I could be asking myself for the partial of z with respect to s. because z depends on s and t. So if I wanted to know that, here's how I would do it. I would go first from z to x, right? So I do that partial. And then I go from x and I need to go to s. So I go down this branch and I do that. So I'm going to have to do this one times this one. So it should be partial z with respect to x times partial x with respect to s. Now, on the other side, I have an s down here also, which means I would have to get from here to y. So I need that partial. And then I need to get from here to s. So I need that partial. I need those two multiplied. And that branch is going to be added to this. So we add to that partial z with respect to y times partial y with respect to s. Do y'all understand why this bottom, why these are partials? You understand why this is not straight dx ds? There has to be a partial here because x depends on something else also, right? So that would be one of the partials I could get. And I believe that matches this one. Make sure there's no typos here. Yeah, okay. Now, if I wanted the other partial, which would be the partial of z with respect to the other variable t, then I'd have to do a little different. I would have to go from here down to x, then down to t. So I'd pick up this partial and that partial. Then I have to go down here, so pick up this partial, and then down this branch, pick up that partial. And then I'd multiply down this branch, multiply down this branch, add the two together. And that's what this is. Make sense or not?
It makes sense.
Okay. Now, I believe I have an example for this one, but we're not going to do it right now. I want to just throw something crazy out there, and then I'm going to talk about the test. Clear this out. Okay, so what if we had this? What if we had z depends on x, y, and t? What if x depended on R1, R2, R3, y depended on R1, R2, R3, and t depended on R1, R2, R3. My first question is, how many derivatives are possible?
3.
3. Okay, can you tell me what they would be? What are the 3 derivatives that are possible here?
Partial derivative with respect to R1, partial with respect to R2, and partial with respect to R3.
Yep, perfect. Partial of z with respect to R1, partial of z with respect to R2, and partial of z with respect to R3. Those are the 3 possible ones. Let's just look at one of them, okay? I'm just going to pick one of these. Partial of z with respect to R2. That means we need to get from z down to R2, right? So to do that, I have to go down this branch and this branch, go down this branch, then this branch, and this branch and this branch. I'm going to figure out what those derivatives are down the branches. I'm going to multiply down the branches, and then I'm going to add up all those things, right? So the first branch from z down to x has to be a partial because z depends on x, y, and t, right? And then down the blue branch here, x depends on 3 things, R1, R2, and R3, so it also has to be a partial. And then when I go down the middle branch, it's partial z with respect to y, and then partial y with respect to R2. And then down the other branch, partial z with respect to t, and then partial t with respect to R2. So this would become those 2 multiplied plus those 2 multiplied plus those 2 multiplied. Does that make sense? Yeah?
Yes.
Okay. What if I changed one thing here? Oops. What if I said, instead of that, that depended on, what have I not used? Q, 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 Q. How many derivatives are possible?
One.
Just one. And would it be a partial or would it be a straight derivative?
Be just dz over dq.
dz over dq is what it would be. Straight derivative, not a partial. Now, think about what it would be, though. It would be, I can't get rid of the blue, so I'm going to have to come in. I'll do green. So it would be, you go down this branch, then down this branch, and then down that branch. Everything down that branch multiplied together, right? Plus everything down that branch multiplied together, plus everything down that branch multiplied together, plus, and now you got to go down all the other three branches here, three branches here. So this would actually be equal to like, how many different things added? Be what, 9 things added together, right? You'd have 9 things added together. That would be a mess, wouldn't it? That'd be a mess. Okay, I have to stop. There's not anything on the chain rule on the test. Let's look at the test. I'm going to bring it up and then we can discuss it. So this is probably a good time for you to just like jot some things down that I say, because I'm going to give you some kind of pointers on this or like ideas. Oh wait, I'm in the wrong place. All right, I'm calling this a midterm. So this midterm, I'm asking that you work alone on this exam. So up to this point, I've been pretty open about you talking to each other on the mini exams and working together. I don't know if you have been doing that, but from looking at people's work, you know, sometimes it's weird when you have a problem that's somewhat difficult and then you have the same like 2 or 3 students approach it exactly the same way. It's kind of, you know, but I'm asking you to work alone, all right? Show all steps, so don't leave any work out, okay? Don't give me just answers. Show all steps and submit clean, legible work. So I expect this to look like you've taken some pride in it, right? And you've organized it and you're ready to present this to me, right? You may reach out to me for help. So I am available to talk about anything. If you have questions, I'm here to help you. You can either text me, call me, text me, or email me in Canvas, all right? If it's possible, if I have time, I'll be happy to meet you on Zoom over spring break, you know, and talk to you about anything if I'm available. I will be here for spring break, except I'll be out on the 12th through the 14th, but I will be available. I just won't be available via Zoom. All right, I don't think I will. This is due on the 17th. So I was thinking about when I wanted this to be due, and I was originally going to make it due on the 22nd, but I think that that's just too far away, only because you'll be so worried about this exam, you won't be focusing on the material that is going to be, you know, due, or that we're going to be doing that week, and it's very important material. So I'm going to make it due the 17th. That's 2 weeks from today. All right. I will send you an email with this test today, and it'll have the Dropbox links where you can upload that. All right. Okay, here's the test. Oh, it's blank, I guess. No. Okay, there are 13 questions. Now let me kind of tell you before I go through these questions what I was shooting for here. This is a mixture of challenging problems with problems that are very just mechanical. So some of these problems are just very similar to like the problems you'd find in the homework and that problems we've done in class. But if you've done any of the mini exams, which I know some of you have and some of you have not, these are the other problems in here are more like the mini exam problems, which means you have to think through these things. You have to understand what's being asked. You have to put multiple concepts together in order to figure out, you know, how to go about the problem. So I expect there to be questions. Now this test is worth a lot, right? This is a lot of points for the class. So you cannot afford to turn in, you know, 7 of the 13 problems here. You need to be able to do all of them. So first one is one of the more challenging ones. Find the equation of a sphere with radius 9. Wait a minute, hold on. The equation of a sphere, and I already give you the radius? So all you really need is what?
The center.
The center. So I'm just asking you to find me the center of this sphere. So find the equation of the sphere or spheres. It could be more than one. With a radius 9 that is tangent to the YZ plane, and its center has to pass through these two planes. Okay, so you'll need to think about that. All right, but at the end of the day, you're just looking for a point. That's all you're looking for is a point. If you can find a point, then you've got the center and then you're done. But it's got to be radius 9 tangent to this plane, and the center must be contained in both of these planes. So I'll let you enjoy that one. All right, find the value or values of t where the particle which moves along this curve, so I give you a vector function, and I'm asking you for what value of t does it have a maximum speed when it's in between the interval of 0 to pi. So this particle is moving along a curve, right? T is changing between 0 and pi, and I'm asking you at what value of t is this particle achieving its maximum speed? And then I ask you, what is the maximum speed? So when does it happen and what is that maximum speed? Okay, next one. If a of t is this nasty looking vector function, if that's the acceleration of a particle at time t, and I give you some initial conditions on the velocity and the position, then I want you to find the distance from that particle to this plane at a specific point in time. Okay, I give you acceleration. And then I'm asking you how far away a particle is from a plane. So if you start with acceleration, you're going to somehow have to get back to position. And once you get to position, they're going to be trying to figure out the distance from that particle on that position function to this plane that I gave you. So this is kind of like 2 questions in one. A lot of these are like that. Next one, this one has always tripped people up. I'm sorry I'm over on time. You can go if you'd like. I'll post this video later if you want to watch it later and listen to me. Okay, so here I give you R of t. It's a position. It represents the position of a particle at some point in time. Right, so you got this position function. If the particle starts at the point 0, 0, 0 and moves a distance of 4 units along the curve, then where is it now? So it's starting at the origin, it's moving along this surface, and it moves 4 units, and I'm asking you to give me the point in space that it's now sitting at. Okay, here's a more like straightforward problem. Find the unit tangent vector to this at some point in time. Unit tangent vector is just their formula for it, and just crank it out. So I'd say like the first 4 are going to be like, they're going to have you thinking for a while, I think. Number 6, find the velocity function of a particle with this acceleration function. So velocity, you can get from acceleration to velocity. This is another pretty straightforward problem. Now, it's going to require a little bit of memory of how things you did in Cal 2, but it's a pretty straightforward problem. Okay, find the domain and sketch it in R2. We did these problems where we looked at these functions and we said, what does the domain look like? And then we tried to draw it. And then I showed you the surface and I was like, look, if you look from the top, you can see it looks like the domain we drew. So that's a pretty straightforward problem also. Number 8, show that this limit does not exist. So this goes back to the last class and maybe the one before that, where we were talking about how it's hard to show that a limit does exist. It's easier to show, it's hard to show it does exist, but it's easier to show that it does not. So I'm telling you this limit does not exist. You just need to show it somehow. All right, so you have multiple options on how to do that. Maybe you pick 2 paths and you get 2 different answers, or maybe you squeeze it. I don't know, you take whatever approach you want there. All right, number 9 is just a gimme problem. That's just like, okay, if you can take the first partial derivatives of that, there's nothing special there, straightforward. Number 10 is kind of like the problem we started class with the Laplace, but that's not the Laplace equation. So I give you a function and I just say, hey, look, show that it satisfies this equation. So the partial of u with respect to t, so when you take the partial of this with respect to t, you get this, which is a second partial. So you're gonna have to make sure you understand what that notation is, what it means, but you need to show that it is equal. All right, that's, again, I think a pretty straightforward problem. All right, 11, find the shortest distance between the point 4, -3, 8 and the plane which is tangent to this surface at this given point. All right, what did we do today? Did we do tangent planes today? We did, right? So if I give you a function and I give you a point, you should be able to give me the tangent plane here, right? And I'm just asking you to give me the shortest distance between that point and that plane that you found. So this is a 2-in-1 also, okay? 2 problems in 1. All right, I'm real excited about number 12 and 13, okay? Find the curvature of the vector function which represents the intersection of those 2. And then 13, I'm not going to talk much about it. I'm just going to let you read it and see how it goes. I will give you a hint though on 13. I'll give you a hint. You're going to have to use Cal 1 in here. Something in Cal 1 that you use to figure out where something has a maximum. Think about in Cal 1 how you determine where something had a peak. Okay. What else was I going to say? Oh, so like this is a take-home exam, right? This is Cal 3. I try and make these so that y'all can't just go Google it or just go look it up on some easy math web thing. I mean, you could type this in, but I seriously doubt if you type the entire questions in that you're going to find any help on the web. So I would not invest time into trying to find the answer somewhere. I would invest time in trying to think through it. And then when you get hung up, or if you have an idea of how to approach it, just reach out to me. I mean, I really want this to be more like I'm trying to help you learn and you have some ideas that you want to bounce off me. I mean, that's the way I kind of want this to be. But see how it goes. Any questions?
So are we able to turn it in earlier than the 17th, like the 15th?
Yes, but I probably won't grade it until everyone's turned it in.
Oh, okay.
And I don't think I'll do anything as far as like you get bonus if you turn it in early because, yeah, I mean, yeah. So you can though. I mean, I have no problem with that. All right. So that's it, I guess. I've got nothing else. Good luck with it. Enjoy your spring break.
You too, sir. All right. Have a nice day.
Yep, you too.
Have a good week.
All right, we'll talk soon.